Alright, so this problem says, suppose you have a coffee mug with a circular cross section and vertical sides. So uniform radius. What is its inside radius if it holds 375 grams of coffee when filled to a depth of 7.5 centimeters? Assume coffee has the same density as water. Okay. So the density is 10 to the 3 kg per meter cube. Density is mass times volume. Mass is density times volume. And for a cylindrical object, volume is area of cross section times height. Like that. So mass is area times height. Okay. What are we finding? What is the inside radius? Okay, so R is what we're trying to find. Okay. All right, so let's put in all these quantities. Mass is 375 grams, 0.375 kgs. Pi rho is 10 to the 3 kg per meter cube. Height is points meters. All right, so what we'll do is we'll make this okay, so we'll make this 10 to the 4 and this will become 0.0075. Okay, so 10 to the 4 coming to the top becomes 10 to the minus 4. Square root of that will be 10 to the minus 2. And the reason I'm doing is 10 to the minus 2 is then the meter to, that will be the meter to centimeter conversion. Okay. So this will be equal to, or I can do 3.75 and 10 to the power 4. Okay. 3.75 pi okay. Did you guys understand that? All right. So, and this is equal to so 4 into 10 minus 2 meters equal to 4 centimeters. So that's the radius of the cup. Okay. Any questions on that? A trash compactor can compress its contents to 0.35 times their original volume, neglecting the mass of air expelled. By what factor is the density of the rubbish increased? So density is mass times volume. Okay. So final density is mass times final volume. And final volume is 0.35 times initial volume. So final density is 1 over 0.35. and this guy is the initial volume. So almost 3 times the initial wall density. You guys see on the highways, on those trucks, they have those crushed cars that they transport. So you saw that the reason for the thicker walls on dams, as you go down, the pressure is increasing, so the force on this face is greater than the force on the same slab there, and that's why the walls have to be thicker to counter that force. Okay. And so a dam is used to hold back a river. The dam has a height of 12 meters. 12 meters is roughly 3 times the height of this room. The height of this building, if you go into the atrium, that's 12 meters roughly. And a width of 10 meters. 10 meters is the width of this room. Okay. Assume that the density of water is 1,000 kg per meter cube. Determine the net force on the dam. So they want you to find the net force, this force. Why does the thickness of the dam increase with depth? You saw that because the pressure increases. Okay. Now the pressure at this point, P at this point is P naught. P naught is the pressure at the surface of the dam plus rho GH. Okay. Rho GH is the height of the fluid. Okay. Now the pressure at this point is P naught. So the net pressure is P minus P naught. Okay, so P minus P naught is what is relevant, rho GH. Okay. Did you guys understand that? Okay, so let's calculate the force DF on that slab. DF is the net pressure times the area of that slab. And the area of that slab is P minus P naught, width of the wall times this height, dy. So the force on this strip, dF, is P minus P naught, which is rho GH with dy. And what is H? H is, this is 12 meters minus y. Okay. So that is that force. And the net force is just the sum of all those things, those little forces. The force on this slab plus the force on that slab plus the force on that slab. And of course, you guys are professional mathematicians, and so dF summation is the integral. Rho G 12 minus y W dy. And what are the limits of the integral? You're integrating over y. Y is changing from 0 to 12 meters. so rho GW is okay, and that's the net force. All right, so the net force is rho GW this limit applied to there is that's 12 square minus again 12 square by 2. No, I'm going to write it here, h square by 2. Okay, so the reason I wrote it like this was, see, this is the pressure of the liquid halfway down the wall. That's the average pressure on the wall. So that's the average pressure, and that's the area of the wall, width times height. So the total force is equal to average pressure times the area of the wall. Did you guys understand that? All right. Assuming bicycle tires are perfectly flexible and support the weight of bicycle and rider by pressure alone, calculate the total area of tires in contact with the ground if the bicycle and rider have a total mass of 80 kg, and the gauge pressure in the tire is 3 times 10 to the power 5 pascals. Okay, so I'm going to do a simplified diagram. So here's a tire. Okay. And here's a piece of rubber that's in contact with the road. Okay, so here's the net weight, okay, acting, and so this tire is pushing the ground down with equal to the weight of the person being supported. The ground is pushing it up. Okay, the ground is pushing this piece of rubber. Okay, so why isn't the rubber flying up? Well, the air in the, okay. So this is the force that the air is exerting, and that's balancing the normal force, which is equal to weight. Okay, so the force of the air equal to the normal force equal to mg. What is the force that the air is exerting? The pressure times the area. That is the area that is in contact with the ground. So the pressure times the area is equal to the weight that is being supported. And now this pressure is absolute pressure because there's no atmosphere there. It's not gauge pressure, but absolute pressure. Okay? So well, maybe we should take gauge pressure because no matter what, there's always air underneath. Yeah, so I think, yeah, we'll take gauge pressure. So this is gauge pressure. All right, so gauge pressure times area equal mg. So area equal to the weight being supported by gauge pressure. All right, so now you'll understand the following. You guys know semis have, well, there are 18 wheelers, right? Trucks have 8. Why do they have 18 wheels?
Support heavier loads.
What's that?
Support heavier loads.
If you want to support heavier loads, the pressure, you could increase the pressure, but if you increase the pressure unlimited, the tires would burst. So there's only so much pressure you can put on the tires. Okay, the greater the load, if this is the same, the area has to be greater. The only way you're getting more areas is by putting more tires. Okay. So whenever you're supporting heavier loads, you're increasing the area, and the only way you're increasing the area is slapping more tires on. Yeah. All right, so this area is, so 80 kgs times 9.8 meters per second. And gauge pressure is 3.5 into 10 to the, that's 3.5 atmospheres. Okay, so in your bicycle tires, actually, so because the pressure is higher than in your car tires. In your car tires, it's 2 atmospheres. The gauge pressure is 2 atmospheres. In your bicycle tires, it's 3.5 atmospheres. Okay, so this area is, we'll say 10 to the minus 4 meters square. Into, and the reason I wrote that is centimeter square. So 22.4 centimeters square. And that's about 5 centimeters, so 2 inches by 2 inches. That's how much area is in contact.
Why did we use the gauge pressure and not the absolute?
Okay, so here's air pushing down, okay? But no matter what, there's air underneath as well, and that's atmospheric pressure.
Okay.
So absolute pressure minus atmospheric pressure. Okay, so that's the gauge. The gauge pressure is what's pushing down on it.
Okay.
So you put a piece of paper on the table. Unless you get all the air out, there is atmospheric pressure underneath. Okay, so this problem says, what force must be exerted on the master cylinder of a hydraulic lift to support the weight of a 2,000 kg car, a large car resting on a second cylinder? The master cylinder has a 2 centimeter diameter, and the second cylinder has a 24 centimeter diameter. So you see, this is a factor of 12 increase. The area increase is 12 square, which is 144. So every pound of input force gets multiplied by 144 for the output force. So you apply a 1 pound force, the output force is 144. That's what those numbers mean. Okay? So there's the load being lifted, and there's the input force. So you saw that the output force is equal to A2 over A1 times the input force. The output force is mg. Okay. Bless you. And area is pi r square d1 over 4 square and of course all the constants cancel. So this is equal to d1 by d2 square mg. That's 2 centimeters divided by 24 centimeters. So to lift this car up, the input force is 1/44 the weight of the car. And so for a 2000 kg car, that's about 14 kgs, which is 14 kgs is 25 pounds. So to lift a 5,000 pound car, you're applying a 25 pound force. Okay. Okay. A host pours the remnants of several bottles of wine into a jug after party. The host then inserts a cork with a 2 centimeter diameter into the bottle, placing it in direct contact with the wine. The host is amazed when the host pounds the cork into place and the bottom of the jug with a 14 centimeter diameter breaks away. Calculate the extra force exerted against the bottom if he pounded the cork with a 120 Newton force. Okay, so essentially the idea is the following. This is the same problem as the hydraulic press, okay? So you're applying a force here, and this is area 1. Okay, so Pascal's principle says if you increase the pressure on an enclosed fluid at any point, that same pressure is transmitted undiminished. Okay, so F1 divided by area 1 is equal to F2 divided by area 2. So the force on the bottom of the jug is A2 over A1 times F1. You press down on the cork with this force, the force you're applying on the bottom is that much. And again, area is So the diameter of the bottom is 14 centimeters, the diameter of the top is 2 centimeters. So the force on the bottom is 50 times the force on the top. So maybe you should try this. We all have wine bottles, but the area multiplication factor is not, so the radius is maybe 3 times. With a wine bottle, you fill it with water and pound the cap down, you'll get a force multiplication factor of about 10 on a flat bottom wine bottle. But if it has a bunt, you'll get a higher multiplication factor. Well, no, with a bunt also. Anyway, with a bunt too, you'll get it effectively the same, 10 factor of 10. Okay, I'm going to try and break a bottle. So if a person's body has a density of 995 kg per meter cube, see, almost the density of water. So in fact, we should all float. What fraction of the body will be submerged when floating gently in fresh water? So 99.9%, 99.5% of the body will be submerged. So the density of the object divided by density of fluid equal to volume displaced divided by volume of the object. Okay, again, this is the volume displaced, and that's the volume of the object. Okay. So 995 kg per meter cube divided by 1,000 kg per meter cube. So this and this is equal to 99.5%. So if this person doesn't panic, there'll be 99.5% submerged and 5% will stick out. And that can be your nose. In salt water, the density of that much. So in salt water, when the density is higher, this number is smaller. So this number is smaller, so less of your body is sunk. So in fact, in the Dead Sea, you probably couldn't drown yourself.
What prefix is that for the first measure of density?
Density of object
Object.
divided by density of fluid.
Thank you. That makes more sense.
All right, so I'll add a J. How's that? calculate the buoyant force on a 2-liter helium balloon. Given the mass of the rubber in the balloon is 1.5 grams. What is the net vertical force on the balloon if you let go? Neglect the volume of the rubber. Okay. Okay, I will do 2 more problems, so we'll be done with this one. So here's a balloon. It's got helium in it, and we want to calculate the buoyant force. All right, the buoyant force is equal to the weight of the displaced fluid. What fluid was displaced? I'm sorry? Air was displaced, okay? So here the weight of the helium plus the weight of the balloon, and there is the buoyant force. And the buoyant force is the volume of air, weight of air displaced, okay? So if this force is greater than this weight, then the balloon will rise, okay? Air volume displaced times G. Okay, so, and density of air is 1.29 kg per meter cube. Volume displaced is 2 liters. A liter is 1,000th of a meter cubed times 9.8. And so this, the buoyant force is so that is the buoyant force. That's the weight, 25.3. This is well, that's 10 to the minus 3 newtons. All right, so essentially that well, divided by 10. Okay, that's 2.5 grams of air that's displaced. Okay, that's 2.5 grams. All right, let's calculate the mass of helium and mass of the balloon. So let's calculate this guy. It's 2 liters of helium, okay? Okay, how do we calculate the mass of this guy? We'll assume STP, so to keep it simple. That's standard temperature and pressure. At STP, what is the volume of 1 mole of ideal gas?
22.4 liters.
Very good, my friend. So, and helium, the atomic mass is 4 grams. So 4 grams of helium will occupy 22.4 liters. Okay, so the mass of helium is 2 liters divided by 22.4 liters times 4 grams. Okay, so the mass of helium you have is 0.089 grams. All right, so the weight you're supporting is mass of helium plus mass of balloon times G. 0.089 plus, and the mass of balloon is 1.5 grams times 10 to the minus 3 kgs times 9.8. So essentially, you're supporting, helium weighs nothing, essentially, okay? So when you're designing these balloons, if it's a, you calculate the mass of the air. If it's a 5-liter balloon, you calculate the mass of the 5-liter air. Okay, so this is 2.5 grams is the mass of air, and your balloon had better weigh less than that. Okay, so essentially that's the calculation. All right. So okay, so this is the weight being supported, and there is the buoyant force. And you can see that the buoyant force is greater than the weight being supported. Okay? And that'll always be true when? That'll always be true when the density of the object is less than the density of the surrounding medium. Okay? So the net upward force is the buoyant force minus the weight, which is 25.3 minus 15.6 into 10 to the minus 3 newtons. Okay, 9.7 into 10 minus 3 newtons. So the helium balloon feels a buoyant force. Okay. Till when will it feel a buoyant force? How? The helium balloon will rise. As it's rising, the density of air is decreasing. It'll keep rising till the density of outside air equals the density of inside the balloon, for the balloon. And so these helium balloons can rise up 30,000 feet and stuff like that. People in planes can see them if they're large enough. Apparently, this is a while ago, a retired postal service guy attached a bunch of helium balloons to his lawn chair and rose up in Los Angeles. Yeah, got into flight paths. He had a BB gun too. Why?
To pop.
Yeah, there you go.
So it go back down.
What's that?
Oh, so you could shoot down balloons so it could go back down.
Yeah. All right, we'll do one more problem and then we'll be done with this chapter. Okay. Every few years, winds in Boulder, Colorado, attain sustained speeds of 45 meters per second, 100 miles, about 100 miles an hour, when the jet stream descends during early springs. Approximately, what is the force due to Bernoulli's equation on a roof having an area of 220 meters square? 220 meters square is roughly maybe twice the area of this room. Okay, so we'll calculate the force on the roof of this room with the wind blowing at 100 miles per hour. What is the speed of air inside the room? 0, if you have all the windows closed. The air is moving faster on outside. Air moves faster, pressure is lower. So the pressure on top is lower than, inside it's 1 atmosphere, outside it's lower than 1 atmosphere. So you feel a net force on the roof. Net upward force. Okay. So that's why during hurricanes you board up your windows, because inside is 1 atmospheric pressure, outside is lower pressure, and the windows would explode outwards. All right, so let's calculate this force. Okay, do you guys understood, yeah. Okay, so here is, so the fluid is air. Okay, so V1 and V2 are points just on top of the roof and just below the roof. So these two terms essentially cancel each other. Inside the room, the velocity is zero, so this term is zero. Okay. What is the pressure here? What is the pressure here? That's atmospheric pressure. Okay. So we have P1 plus 1/2 rho V1 square equal to P naught. Okay, so P naught minus P1 equal to 1/2 rho V1 square. Okay, so the net upward force so times the area of the roof. All right, so now we can put in the numbers. So the net upward force is 1/2 rho. The density of air is 1.29 kg per meter cube. In Denver, it's slightly lower, but we won't worry about that. The speed of the wind is 45 meters per second. And area is 220 meters squared for the roof. And so this works out to okay, that's that much force. Okay, to put it in perspective, so force is mg, divide that by 10, that's 10 to the 4. That's 1,000 kg would be a car, so that's the weight of 30 small cars. And that would be the upward force. What is the roof held down by? A bunch of nails. Yeah. So I would imagine the insurance companies will make sure that your roof is tied down real good before they'll sell you insurance. Okay. All right, guys.